Hello, everyone. So I'm going to be speaking about combining the power of high throughput calculation, ab initio calculation, and machine learning, and to go in the direction of what is called materials informatics. So I took an historical point of view. So namely, I mean, if we think about the methods and the concepts that we have in materials science, they have evolved through time. And if you think about the discovery of fire, it was just by, chance that we discovered it. Then at some stage, we thought it was one of the elements that was constituting everything around us, like water, earth, ether, air, and fire. And then we realized that it was, sorry, because I'm losing the control when someone enters. And so we realized that it was actually excitation of molecules and de-excitation were emitting some light. And so, in fact, this approach that the concept that we have, one of them is the experimental research, and the experimental research dates back to the Stone Age. We've been testing things, and the trial and error method is something that we've been doing always, basically. And still, in material science, this is something that we continue to do. And I take the example here of Edison. When he had to decide about the materials of the bulb lamp, he tested something like 3,000 materials, including the ears of his assistant. And an important point here is that in the end, the material that he chose was not tungsten because simply he didn't try it. Okay, so you see that the trial and error has some intrinsic limitations. You can only find what you try, you cannot go beyond that. So this trial and error and empirical approach is what is called the first paradigm of material science. Then with time, we started to establish relationships of physics describing the laws of what we're seeing around us. In the field of material science, it's trying to establish relationships of cause and effect between the process that we apply to get one material, the structure that we get for that material once we have done the process in that way, and the properties that are related to that structure in such a way that in the end there is a given performance for the application that we are targeting. Then there was a big transformation that happened due to the appearance of computers and supercomputers. And so this revolutionized the world. And so when you look at the first machines that were found in 1945 compared to the one that we have nowadays, you see the enormous augmentation in terms of the number of flops that are available, and the cost is not much more expensive. There is some order of magnitude, but it's nothing compared to the power that we have. And this has led to the possibility to go in the direction of the so-called virtual experiments and the simulations basically we do. And so it's the third paradigm of material science. So we had empirical, theoretical science, and then computational science, and with methods like molecular dynamics, density functional theory, and so on and so forth. And all these allow us to do the experiments not anymore for real, but in the machine. And I am coming, like Hongbin, from the realm of first principles. And if you look at the different methods for making the simulations, they vary in length scale and in time scale that can be simulated. So we have the first principles that allow for a limited number of atoms because they deal with a very good accuracy with both the atoms and the electrons. When you move to molecular dynamics, you don't treat the electrons explicitly anymore, and so you focus on the relationship between the atoms. And this allows us to scale, to increase the time scale for the simulation and to increase the number of atoms or the length scale of the simulation. If you want to go beyond that, you need to not treat all the atom explicitly anymore, and you can treat beads of atoms consisting of a bead with several atoms together, and this is what is called coarse-grained molecular dynamics. And then finally, if you want to go to even larger scales, so scales that are typically the one that we start to be able to see with some microscope, for instance, and scales that are reasonable, then you have to go to the fact that you don't treat the materials as being made of atoms and of course not of electrons. And so you treat them as a continuous, and that's the methods of finite elements. So in the fields where we're coming from, so ab initio calculation, there has been many improvements with time, compared to when I was studying my PhD thesis, and now there's been a huge increase. And now, in particular, the codes that we have and the power of the supercomputers make it possible to do what is called a high throughput screening, and so high throughput ab initio design of material. So typically, the idea is the following. Sorry, I have to again to fight with the. Here we go. Um, so the story is the following. We consider typically of the order of thousands and even hundreds of thousands of compounds. And basically, we do the same thing as Edison was doing. But instead of trying in an experimental way, we compute a number of properties for each of the materials that we consider. And so basically, if the property that we compute at the first stage is okay, we move to the second stage, we compute the property. And if it's okay, we move to the third stage, and so on and so forth. And you see that sometimes some of the materials meet the requirements in terms of all the properties that we have computed. But most of the materials, as you can see, they end up in the bin. And so out of the thousands or hundreds of thousands of compounds that we tested, in the end, we're left with 10 to 100 compounds, which we can give to our experimental colleagues that can either synthesize it or characterize it. And if we did a good job in predicting the different properties, they should have a material that meets the requirement for the application that they had in mind. So here there are two things that are important. So there's the high throughput approach, and so there's been huge efforts in developing workflows to make all these calculations as automatic as possible. I won't say too much about that today, but if you have questions, I'm happy to answer with that. And the other part is, as I said, there's many materials that end up in the bin, but we don't want to lose all that because in the future we want to do some data mining, and I will come back to that in different ways. So, but before going that, I'd like to give you an example of such a funnel in which we screen something based on different properties. So the example is the following. Well, we're looking for materials with a high carrier lifetime and that are defect tolerant. And so these are good solar absorbers for photovoltaic panels. So we need materials for when you create the electron hole pairs, it doesn't recombine too fast, and you can move the electrons and the holes to the two cathodes, anodes and cathodes. Okay. So in this case, this work, we considered 8,000 compounds made of copper, and we computed different properties. As you can see in the funnel, some of the properties appear twice. So for instance, if you look at the band gap that appears at the top, it's also at the second layer. And you may wonder why we compute it twice. It's simply because we computed it with two different accuracies that are indicated by the colors or the symbols of the lines around the boxes that you see. So you see that the top one is computed within PBE, which is a given level of approximation. And then we have HSE, so PBE is known to underestimate the band gap, but then we do a calculation with HSE, which is much more accurate. And while it is difficult to do such HSE calculation for 8,000 compound, it is perfectly doable for 75 compounds for the band gap there. And you can even go for more involved calculations, such as point defect, the calculation of the capture coefficient, or even the intrinsic mobility when you have less and less compounds. So this is really the idea of this funnel, is that you try to screen at the very top the easy properties to compute in such a way that you reduce the number of materials, and so that you compute the other for a limited number of compounds. So in the end of this work here, we had found 6 compounds, but I don't want to go into the details of that. And I just wanted to put on the right-hand side another plot in which we were comparing, looking at our theoretical efficiency as a function of different criteria also that are related to the production of the material. So one is the so-called HHI index that tells you how spread the production of the material is. So if it's not located in only one country, which can lead to some difficulties as we see in the world in which we live in for the moment, it is a good thing if this production is widespread. So that means that the HHI production index is low in this case. And the other thing that you see is the color of the points. So there's the MC is the materials companionality, because some of the materials, of the elements, when you extract them from Earth, you get another one for free. And so here, having a materials companionality that is low again is a good sign. And so in this case, you see that the material that is at the top left, so sodium copper phosphate, is one of the most interesting because it has a low HHI index, and at the same time, it has a small materials companionality. This is just to illustrate the concept of the funnel. And once you have done that for a funnel, it's not difficult to put more materials at the top of the funnel. And that's what we did. And we moved to an example in which we screened all these compounds for 4,000 inorganic materials. We extended that beyond the copper material, and we could even include some stuff related to the cost of the material. Because again, when you want to do something in industry, you need to pay attention to the cost. And so a material can be very interesting from a fundamental point of view, but from an industrial point of view, the cost is really important. And so we can take that into account again as a screening parameter. And in this case, this material that is here, this barium cadmium phosphide was quite interesting both in terms of cost and in terms of the predicted efficiency. And so we could give that material that we discovered there to our experimental colleagues that were able to synthesize it, and then they made the measurement and confirmed what we had done. Okay, so I'm not going to spend too much time. I wanted more to tell you about the idea here. And actually, there's an a method, the screening approach that we applied in many different fields like transparent conducting materials. We looked for electrolytes. We looked for high refractive index with wide band gap, high Curie temperature, thermoelectrics, multiferroics. And actually, we were not the only one, of course, to do these kind of things. There have been many groups that did that. And if you remember my animation that I showed before, many materials ended up in the bin. And of course, this is something that you don't want to lose. And so people started to create online databases with a number of properties that were available in each of these. And so this is, you have material databases that you probably know, like the Materials Project, the Materials Cloud, Nomad in Germany, A-Flow, COD, and so on. So there's many databases that have become available with time and that are still growing nowadays because we can continue, thanks to the development in terms of workflow that were done, we can continue to populate these databases with more and more properties for the materials. The nice thing that has happened also is that all these databases joined together and they developed a common API that is called Optimate, and that allows you to query all these databases with the same exact query. So you don't need to change and learn the API of each individual databases. You can use the same API. So basically you need just to know the endpoint of each of the database. And we even have a website where you have all the providers. So you just need to change that. And then there is a part that is common to all the rest of the databases. And you keep that part once you have defined the filter and you apply it to different databases. And so you can get responses from all these other databases at the same time. And as an added value, we have developed a number of Python tools that make it easy to add new databases. And so you probably know Alexandria, the work of Miguel Marquez and Silvana Botti in Germany. And this was one of the latest databases that was added to Optimate, and that was done very easily, and it's accessible very easily in the same way. So for your reference, we have published a number of papers. The first one was in 2021 with this first specification. Then there was a paper about these Python tools that I just mentioned. And then in 2024, we published the new version of the specification. And now version 1.3 is just out. We still haven't published a paper about that, but it will take some time to publish the paper, but still the version is out. And so this gives you a nice tool to gather data. So coming to this, back to this idea of the high throughput ab initio design. So one of the main problem is, of course, that we need to do the DFT calculation. And so we're limited both in terms of the accuracy of the DFT, and we're also limited in terms of the computational cost. So, many of the properties that we have compute can require some CPU time, and so that can become a significant bottleneck. And obviously, there's another limitation, which is exactly the same as the one that was underlying for the case of Edison, which is the fact that the search is limited by what you put in the funnel. Okay, so Edison had chosen a number of materials. In our case, let's say that usually we take data that is coming from experiments. or from some of the other computational databases. And then we have something that we can do quite easily compared to experiment, which is to do virtual substitution. It's very easy in an input to take an atom and to replace it by another. And these things are usually done based on our ideas, intuition, but these can, may be biased. And so it's important to go beyond that. And this is where moving to machine learning is probably the way to go, in the sense that we are now entering in the fourth paradigm of material science, which is the data-driven data science. And using all these data that have been generated helps us to do things that will make it easier to screen all these materials and even to go beyond the screening. And I will say a few words about that also. So one thing that we can do with this machine learning is remember that we're trying to establish science relationships of cause and effect between process, structure, properties, and performance. One easy thing that can be done, if we have enough data for each of these relations, we can establish a surrogate model that predicts, let's say, for instance, the property as a function of the process, the composition, and the structure. Okay. And this will help us to screen many more materials than we could do just by using DFT, simply because once this relationship has been established, it can be obtained, the result can be obtained, within a snap of the fingers compared to the calculation that need to be done within DFT. However, there's a problem in that, is that, of course, we need data, okay? And so while the traditional machine learning models like random forest and stuff like that can usually get reasonable results in terms of predictive power, so this graph is the predictive power as a function of the amount of data, traditional model, as I said, can usually get good result even with a limited amount of data. It's a reasonable accuracy, but it saturates quite fast in terms of the amount of data. If you want to go beyond that, you have to use neural networks, but to get better results than the traditional models, you need to increase the amount of data. And if you go to graph networks, which have an even higher predictive power, you need even more data. And the problem is that typically to get more data, is difficult for the data that for the properties that are computationally demanding. So when I have properties that are easy to compute, I have plenty of data. But when the property is difficult to compute, I have, of course, way less data. And add to that the fact that often we have a compromise between the quantity of the data and the quality of the data. I was telling you before about the band gap. If I compute my band gap with PBE, it's a lower quality than with HSE, but it requires much more time to do an HSE calculation compared to the PBE. And so I will have way more PBE than I will have HSE. And typically, if you look in the databases, these are actually all numbers from the materials project, but the situation is roughly the same nowadays. If you look at the properties that have been computed, some of them are quite fast. So the bars that you see there are the time that is needed to compute the structure, the chemistry, the electronic properties. But then when you look at elastic properties, piezoelectric properties, the time required is much more important. It's a factor of 6 to 10, something like that. And so you will not be surprised to see that in the pie chart that you have there, there is way more information about the properties that are easy to compute compared to those that are much more demanding. And just to give you an example, this is a graph where we computed the properties, the nonlinear optical properties, so second harmonic generation, for a number of materials, and the calculation that we could afford were of the order of 600 materials. So that was what we could do, let's say, in a reasonable time. And of course, when the time that is needed to compute such property is important, you want to be very careful in choosing the materials. And so what I will be showing you later on is how to adequately choose the materials that are the most relevant for you, basically. So in order to deal with this paradigm of this contradiction between the quantity and the quality of data, one of the first things that we did in my group was to develop a ModNet, which precisely aims at dealing with data sets with limited data. So the idea of ModNet is that we generate many features, and then we perform an automatic feature selection that is based on a score related to the relevance of the features and the redundancy. We want to choose features that are strongly related to the property that we're trying to predict, but at the same time, they need to bring new information with respect to the features that we had already selected. So this is the redundancy that we want to avoid. And so we made that in such a way that when you benchmark that compared to other methods, so in this graph that you see on the left-hand side, so this is MathBench, first of all, first starting from the right-hand side. So MathBench consists of 13 different data sets. There are 10 regression and 3 classification. Some of the tests require to know the structures. Some are based only on the composition. And then the important point is the number of samples. And you see that there are small data set with less than 1,000 data. And then you have big data set with more than 100,000 data. And then you have different kinds of property that can be computed. And so on the left-hand side, you have the comparison of different models. And so what you see is a scaled mean average error, and the reference is a dummy. And the dummy is basically an algorithm that, takes a random number to make the prediction. And so you have a logarithmic scale, and the lower you are on the scale, the better. That means that your error is small. And you see that Monet, which is in orange and purple, is doing a very good job. And in 4 of the tasks, and even 5 of the tasks now, it is leading the math bench. And actually, we have a paper that is just out on NPJ computational materials, where we are adding more feature, and we have even more of these data sets in which ModNet is leading. Okay? So this is really something that works, especially for small data sets, because when you go to larger data sets, you would see that the convolutional graph networks are doing a better job. Okay? The other thing that we did with ModNet is that we introduced a probabilistic version of it. And so this is based on creating an ensemble of models and making not only one prediction, but a series of predictions in such a way that we have an average value for the prediction, but we also have a confidence interval based on the standard deviation. And this confidence interval can be seen as an uncertainty on our prediction. And once you have the uncertainty, you can go into Bayesian optimization. The idea is to try to predict what is the next simulation that you need to do. And so in our case is how do we determine, let's say in the case of the second harmonic generation, what is our next DFPT calculation? So DFPT is usually way more demanding than DFT. And so we want to determine what is the best way to choose the next DFPT in such a way that will limit the CPU time that is used to do the calculation. And so we can enter into a so-called active learning loop. The idea is that we have a set of data, we train a model, based on the model and optimate, we query many different structures, and we try to determine which ones are the most interesting. Once we know the ones that are the most interesting, we perform the DFT calculation. So that's what is called annotating the data in terms of machine learning. And we append this new data to the existing data in such a way that we can get a better model. Okay. And so now I'm going to give you 2 examples in which we did that and that were published last year. So the first one is about finding materials with a high refractive index and a high band gap at the same time. So the high refractive index is interesting for improving the performance of optoelectronic devices and increasing the response in nonlinear regime, as I will show later. And then the high band gap guarantees the transparency, and it allows the devices to work at higher temperature and larger voltages. So a few years back, we had obtained, by doing a high throughput calculation, DFPT, for 4,000 materials, we had obtained the refractive index for a bunch of oxides, sulfides, and different classes of materials. And at the time, we had spent some time in developing a physical model to explain this dependence that the refractive index decreases with the band gap in a more systematic way. So there were existing models, but we did an improvement compared to that. And we showed that basically there were 2 things that were important. There is an average optical band gap, this omega g that you see in the formula. And then there is an effective frequency that basically describes how for a same band gap, you can increase the refractive index. And this one is related to the oscillator strands and the density of states that are available around the band gap. And so you can see that for a given band gap, we need to increase this omega f to have a larger refractive index. And so the question we try to address here is, can we move the Pareto front of the data that we had by using machine learning? Or in other words, can we increase for the same band gap, can we increase the omega f? So the first thing we did is that we developed a Mondent model to get the refractive index as a function of the structure of the material. And so we compared that to our DFPT data. So the color that you see here is the different folds that I used to compute the mean average error and to compute and to compare with the DFPT. And you see that the agreement is rather good, even though in some cases, especially when there is few data in the beginning, you will have worse results. And so based on this model, we queried the materials project with Optimade, and we determined the materials that were the most interesting in terms of having a high refractive index. And then we computed the refractive index with DFPT, and we compared these new results with the predicted value that we had obtained. And as you can see, it's, in quite good agreement. So we did that many times. At the beginning, there was a large uncertainty. So this is the application of our model to the complete materials project. So this is what you see there in light blue with error bars that are rather large. And so at the first round, so these are the materials that were selected, and we computed the DFT, the refractive index for those. You see that in some of the cases, the value is not on the Pareto front, so it's below the Pareto front. So there may be two reasons for that. One is simply that the model was wrong, and the other is that when we are looking at the determination of the next data that we want to compute, there is two modes in the active learning loop. One is the so-called exploitation that goes at the Pareto front, and there's the exploration mode that goes where the uncertainty of the model is the largest, in such a way that we try to overcome the limitation of the approach that was developed by Edison, so of going in places that we didn't think of. If we go in place where the model is uncertain, that means that these are regions that have not been very much explored, and it's worth to spend some of the time there to see if maybe there is something interesting there. So this is the first round. Then the second round is going furthermore on the Pareto front, and so on and so forth. And after a few iterations, you see that the uncertainty decreases drastically. So the model is getting better and better. And so we can turn to a different database. And in this case, we decided to go for Alexandria to have even more new materials to test. And so you can do this loop a few times, again, even for Alexandria, you see. And in the end, we clearly have an improvement of the figure of merit. So this omega f that we had before. And just a way to show that to you is our initial data set. So that's the N19 that you see in the inset of the figure. The P17 was a previous data set from the materials project. You see that those had an effective frequency that was around, let's say the mean one was around 12. And by our calculation, which is called T14 in green in the plot, you see that it's been moved to higher frequency. And so we literally have moved, we managed to target the Pareto front. And so we limit, by doing so, we limit the amount of calculation that is needed to go where we want to go. To give you another example of this approach, let me speak about these nonlinear optical properties that are important for a number of applications. So one of them is, so the second Harmonic generation is basically you shine some light on a material, and then the light that goes out has a double frequency. And so this is what was used for a long time for getting green lasers. You would shine some red line on the material, and then you would get a green light outside. So in this case, again, based on the 579 data that I showed you before, we tried to develop a machine learning model. And the least that you can say is that in the beginning, it was not very good at all. As you can see, large uncertainty and not very good prediction. But it turns out that it was sufficient to start the active learning loop. And why is it so? There's two reasons for that. First of all, the error. So you see here on the right-hand side, so what is called the index of the model is the different iteration of the active learning loop. And you see on the top that the root mean square error is kind of systematically decreasing. The jumps that you see sometimes is that in the process, we sometimes change the way in which we determined this, so the acquisition function that I was telling you about. We made some attempts to try to select better material, and it was not always a good idea, as you can see. But the main important point that I wanted to make is that the reason why it works is that from the beginning, you have the so-called Spearman coefficient that is already quite good. So the Spearman coefficient measures the ranking that you make. So it measures the order in which the materials are one with respect to another. So you can make a bad prediction, but the ranking of the candidates is good. And so not only it's good in the beginning, but it further increases with time. Okay? So the reason why it works in the beginning is that it's not that bad, despite the root mean square error is big, bigger at least. So in this case, so in the beginning, there were way more results that were kind of wrong, not on the Pareto front. Okay. So you see this, we started from the blue points, the T0, and then SHG 25 is what we obtained. And the red ones are those that are close to the Pareto front. And so in the Pareto front here is some kind of fit that we did on T0. And just to show you the amount of data that we managed to get there. So the original data set is in blue again, so that's the T0 here. The 0 is the Pareto front, and the distance, the delta D is the distance to the Pareto front. So positive distance means that you are below the Pareto front, negative distance means that you are above the Pareto front. And so you can see that the green is much more populated around and above the Pareto front. So another point that you may raise is that in what I told you before, the band gap computed with semi-local functionals such as GGA or LDA is usually underestimated. And of course, this band gap has an effect on the optical properties. So one of the things that we tested is using a scissor shift to compute the second harmonic generation. So the original data set with an LDA is in green, and the one with a scissor corrected band gap is with a different color. And the different color is based on the correction that is applied, and the correction is calculated by doing an HSE calculation on 700 compounds. And so you see that there is a shift to higher band gap and a small decrease of the coefficient due to the increase of the band gap. But the good news again is that when you look at the comparison of the data that you had obtained using purely LDA and the HSE corrected band gap, you see that there's a clear trend between the two. And so it's kind of easy for a machine learning model to learn the correction, actually. And so you see that, okay, there are many ways to try to save as much time as possible, especially if you try to, find new interesting materials. So again, I just would like to insist a bit more on Optimate by showing you that thanks to Optimate, it's very easy, to query new data sets such as GNOME that was released by Google DeepMind, or new data that come in Alexandria at different stages, because you can do the work at some stage, and then 6 months later, you use the same queries that you had, and we have features in Optimate to see what is the changes compared to the previous query that you made. And so you can look at the data that you didn't have before, so the new data, and you can focus on this new data. Okay? So it's very easy, thanks to Optimate and with machine learning models, to query large data set and to try to identify which are the most interesting materials. The difficulty that we have is simply that you need to have a good machine learning model, and this can be improved by this active learning loop that I just showed you before. And such active learning loop can, of course, be done also with experimental data. Okay? So with that, I was telling you that one thing that we can do is to establish these relationships of cause and effect between these steps, the process, structure, properties, and performance. And my focus so far has been mainly between structure and properties. And given that on being mentioned the ERC synergy, the idea there is precisely to go from the beginning, because we want to synthesize the materials. And so we want to use the same kind of approach with processing as well. Okay. So in our field, machine learning has also been used quite a lot recently in the direction of bridging the different scales that I was showing you before. So, I'm coming from the realm of first principles, and we had been doing at the time ab initio molecular dynamics. And I can assure you that in that case, the dynamics that we were able to do were really little in terms of time scale and the number of atoms that we can do. But recently, there's been a development of the so-called machine learned interatomic potential that really helps you to get molecular dynamics at roughly the same accuracy as the one of the first principle calculations. Okay. In the past, for molecular dynamics, one would use semi-empirical or empirical potentials, so with the limits, in terms of accuracy. But now the accuracy that we can reach with these all-atom molecular dynamics is roughly the same as for the first principles. And my guess is that the parameters that you need to do coarse-grained molecular dynamics or finite element will be determined by making simulation at a lower scale and using machine learning. Okay, so this is the approach where machine learning is accelerating things that we're doing before with DFT or different kinds of simulations. But still, the space to be explored is so large that it would be impossible to go in that direction. Just to give you an example, in the ERC that I was mentioning, we plan to stack materials, 2D materials, so it's about phyllosilicates. And if you take three kinds of materials, so three kinds of layers, and you want to stack them and create a material with 15 layers, that's 10 to the power of 17 different possibilities. So if you want to screen that, even if you do 1,000 in one day, it takes several years. And when I say several, it's about 40 years to screen all the material. So that's basically, undoable. And so we need to reverse this science relationships of cause and effect to have engineering relationships, and this is really important for industry, of goals and means. We have a target in terms of performance, and we want to determine what is the process. We don't want to screen all the process. We want something that tells this is the process that I need to apply to get that structure and to get that property and so that performance. Okay, so we want inverse model, and this can be achieved by what is called generative AI. Probably the example that is most well known about generative AI is about pictures. We have so many pictures of people that we have been able to identify what is called the latent space. So the latent space is the small dimensional space that retains all the information that, that in this case is able to describe the face of the person. And so in the picture that you see at the bottom left, you see that, okay, it's an exaggeration. It's a latent space of 2 dimension here, basically, so that's very small. And I mean, the actual latent space is much bigger, but it's just to show you what can be done. And in that latent space, you can label the points as men and women, if people know a number of those. And then you are able to identify a direction for masculinity or for femininity. And so you can increase or decrease the masculinity or the femininity of a face. And so as you can see in the animation, you can go from a man to a woman in almost a continuous way. Okay. And you can do that in terms of also making the person older, making it, changing the colors of the hairs and so on and so forth. So in terms of pictures, we're really able to control all that. And this is what we would love to be able to do with material, controlling the properties by just, moving in that latent space. So in terms of materials, we're way less advanced than what exists for the faces. And one of the best things that has been done so far is this MetaGen that was published basically 1 year ago by Microsoft that is able to produce structures starting from scratch. Okay, so this is the work that they did. More recently, on our hand, we had started something, roughly at the same time, but we're not Microsoft, so we take a bit more time than them to release our stuff. Our idea is to consider weak of position and to develop an invertible representation for the structure based on weak of position. So we're focusing on crystals. And so the idea is that you take a given composition. Based on this composition, you decide about a space group. For a given material, you know the space group, and then you know the lattice parameters, and then you know the a week of position for that material. Okay. And so we associate a number to each of the week of position, and you know the value of the parameters for that week of positions. Finally, you compute the energy above L. And so in the end, your material can be described by a series of tokens. We have a ternary that has a low energy above L. It has this composition, and then it has this space group, and then it has the weak of position 39, 518, and 106, and the values of the parameters of the different weak of positions. And then finally, we have the lattice parameters. So we have developed a language for that. And you know that it is possible to work with transformers to better reproduce languages. And so in our case, we exploited the fact that, in fact, it turns out that the number of week of position is determined. So there's a fixed number of position for the week of, and the distribution of the parameters within the week of position is not random. There is something to be learned about the distribution of the atoms, of the positions in the week of position. Just to give you an example, here you see there's many of them, but if I zoom, for instance, here on the space group, on the cubic space group, you see that in the cubic space group 225, for some of the positions, there's clearly peaks in the positions, in the week of positions. And so this is something that, based on data, the machine learning model can learn. And so this is exactly what we did. We used a transformer architecture. So the name Matra Genoa is Materials Transformer that comes from here. And so we used the Materials Project and Alexandria dataset to train it. And we use a Boltzmann distribution with a parameter T for the generation. So in the same way as when you use ChatGPT, you can tune the let's say the eccentricity of the model by increasing the possibility that it makes wild guesses. Okay, and so that's the same here. So the generation pipeline is as follows. So we first generate the data, and then we relax them with these machine learning potential that I introduced before. And in some cases it fails, but that's fine because we're speaking of a huge amount of data that are generated. And depending on the parameter, if you have a low level of, how to say that, variability in the prediction, you have a lower success rate in terms of uniqueness and novelty. If you increase that, you have more novelty and uniqueness. But if you look at the energy above L, it's the other way around. So if you have a low value for the T parameter, you have way more chances to be close to the L. And if you have a high one, you have a smaller probability to be close to the L. So it's a parameter that you can play with to have more strange structures or more stable structures. So typically what you see here is that if you increase the T, you have a larger count of data, a lower count of data when you increase it that are close to the L. But the nice thing is that even with a larger value of T, you are doing a better job than just doing a random search. You see that we predict many structures that are close to the L. So the paper is on the archive and it's going to be published in the coming days. It's actually already released on NPJ, but it's the temporary version. And so what we did is that we generated 3 million of structures. We selected the 15,000 structures that were the closest to the L based on machine learning, and we performed DFPT calculation. Some of them didn't converge, and so we ended up with 13,000 DFT calculation, and 12,000 of those were close to the L, less than 50 millieV above the L at most, and 4,000 of those were really close to the L or on the L. Okay, and so that means that we have discovered this number of materials. So the Matra Genoa model is available on the web. You can go there and you see that the creativity, so that's the word I was searching on before. So the creativity is my T parameter that I had before. You can put it to small or large. And if you put sodium chloride there for the composition, if you put it to a small value, you will get the usual sodium chloride. But if you increase it, you may get strange structures for sodium chloride. And basically, you can get an energy that is estimated with a machine learning model, and you can get a SIFT that you can download. And so with that, you can try to find structure for a given composition. And the future is to try to also go in the direction of going for structures that are generated with a given property. And in the framework of our ERC is to predict the process condition that lead to that material. And with that, I'd like to thank you for your attention. And I'd like to thank my collaborators on this, Victor Trinquet, who's a PhD in my group. Pierre-Paul was a former PhD and as a postdoc in the group of Miguel Marquez. And the other ones are, well, Miguel, of course, is a collaborator. And then the other two are previous postdocs that were in my group. I also would like to thank the developers of all the different tools that we use, because we're not the only one that develop. We take advantage of all the open source software that is available in our community. I would like to thank you again for your attention, and I just would like to advertise a journal, AI for Science, that's released by IOP Publishing, and I am the chief editor, and we are calling for papers in the journal. Thank you very much for your attention, and I'm open to question, obviously.